Hi class, it's Bill back with a continuing video series from week 11. We're nearing the end of our course. Got a couple more topics, and we talked first in this series about priority queues. We talked about what they are, and then we also talked about the fact that they can't be implemented as easily as we'd like with the technology that we know so far. For instance, an array list really isn't quite up to the task. So we talked about the fact that we'd need heaps, and now we need to investigate those a little bit, understand a little more about them, and then in a subsequent video we'll get into their methods and etc. and then finish by talking about heap sort. So let's jump down and start talking about heaps. So heaps are an interesting data structure, as we're going to see in how they're implemented later versus how we conceive of them. They implement ordering, but they do it in a different way than we have done before. They don't do it by sorting an array list, and even though we're going to show them as trees, they don't really implement sorting the way that we would classically think of doing it with a binary search tree. So they are kind of interesting animals, which is why we're covering them a little bit late. So what are they? They are a binary tree, that's true. They are a binary tree, but their rules are not the same as a BST. It is not a binary search tree, right? They do a little bit less rigorous ordering. Let's talk about why. There's two types that we'll see. There's a min heap, that means the smallest values on top, and there's a max heap, that means the largest values on top. So for a while we'll just use min heaps just so we don't keep confusing ourselves. In a min heap, again, smallest values on top, and any children that are under that must be greater than or equal to the parent. Dupes are fine, but all of the children are certainly no less than the parent. Notice that doesn't mean the left child is smaller than the parent and the right child is bigger, nor does it imply anything about the ordering of the left child versus the right child. It just means that it is at least as big as the parent, so that's kind of interesting. Again, duplicate's fine. If it's a max heap, maximum value goes on top. The other thing that's big, important about this is, yes, we have to understand the ordering rules, but also heaps have a certain shape. And that is that every level in the tree, level meaning a horizontal plane, right, a horizontal cross section, every level must be filled from left to right. There can't be empty spaces in the middle there. And the term that we use for that is to say these are called complete trees. So heaps must be complete trees, and if it's a min heap, there's a certain ordering that you expect in the nodes. So let's take a look at some samples and see if you can find the valid min heaps from the ones that are not valid. So let's see. So take a minute, pause the video maybe, decide which of these are valid min heaps and which ones are not. So let's take a look at the first one. What do you think about that? The shape looks okay, but if you look at the numbers, let's see, 10, smaller, yes, yes, oops. We have a problem here because the 15 is smaller than the 20, so these should not be in this order. If we swap these two, that would be okay, but we can't have 15 and 20 organized this way. So that is clearly not a valid min heap. Okay, how about the second one? Well, the second one, you don't even have to get to looking at the numbers to see that something's wrong here. This is not a complete tree. This level is fine, this level is fine, this level's fine, but this level is not filled left to right as it's supposed to be. This can't be over here. It has to be over here attached under the 40, and then it could be valid. So this is also then not a valid min heap because it is not a complete tree. How about the next one? Take a look. Well, right off the bat, we see a problem right here. The 10 and the 20 can't be in that order. This is not a min heap if 10 is below 20. So obviously that one is also not a valid min heap. Okay, how about bottom left? What do you think? Shape looks right. Numbers, sure. We look at the numbers, they all seem to be following the right path. So yes, this one is a valid min heap. How about the next one? Small, 10, 20, it's a complete tree. All the numbers seem like they're in line. That looks like a min heap. And this last one, well, shape is wrong. Again, this can't be over here. It has to be filled from left to right, so it needs to be here instead. So because this is incorrect, this one is also not a valid min heap. Make sense? All right, so now let's talk about, given those properties, what can we get out of this in terms of efficiency? Well, the height of the tree, notice these are always going to be balanced because of the way that we fill them, right? So by nature they are balanced. That's kind of nice. That means we are going to have kind of a log n situation going on here. So for instance, adding a node is going to be easy. Now we haven't looked at the algorithms. We'll look at those in a minute, but add is going to be a log n algorithm. Peak is going to be easy. Why? Because peak is always going to look at this node. This is the smallest value, so you don't have to go anywhere to find the smallest one. And remove is also going to be a log n complexity algorithm. So these are pretty good, right? This is pretty good efficiency. Now, if you had to search, of course, it takes a little longer because we don't have quite the same capability of going very directly as we do with the BST, but that's okay. We don't tend to do that. That's not what priority queues are made for. So those are all properties. That gives you a good introduction to how heaps work in general. Now we do have to talk about a couple of methods, and they get really interesting. How do you add? How do you remove? So we'll talk about those next, but hopefully this gives you a good start at understanding what heaps are and some of the terminology behind them. So thanks for watching this video. Pick up the next one and we'll go over the algorithms behind add and peek and remove. Thanks.